let's continue. So today we are going to cover oscillations. Okay, so why so? So this chapter, oscillations, it is important considering it has some weightage in itself, and there are other chapters which depend on this chapter. Okay, so waves is one chapter. Okay, then electromagnetic waves is another. Then there is wave theory of light. Okay, or you can say wave optics. So if you don't understand oscillations, then you will not understand any of this. Okay, that's why this chapter is important. Okay, so let's talk about this. So let's suppose you have this block, okay, connected to a spring, and you displace it. What will happen? There will be some restoring force generated in the spring which will try to restore it back. Okay, and this is the Hooke's law, that this force is directly proportional to the displacement, but it acts in the opposite direction. Okay, so force is directly proportional to displacement, but it acts in opposite direction. Okay, the force is called as the spring force, and this law is known as the Hooke's law. Okay, Robert Hooke, British physicist, he had given this law. So if you remove this proportionality sign and substitute an equality sign, so a constant will come in. The constant is suppose k. So this constant k, it is known as the spring constant. All right. So now you can substitute force is equal to mass into acceleration, and you can take mass on the other side. So you get a equals to minus k upon m times x. Okay, and then as you know, the velocity can be written as dx by dt, okay, rate of change of position with respect to time, and the acceleration can be written as what? 2 times of rate of change of position with respect to time, because it is derivative of velocity with respect to time. Okay, so we can write acceleration as d2x by dt square. That means you take one derivative of position with respect to time, then you take another derivative. Okay, so then you arrive at d2x by dt square. So d2x by dt square equals to minus k upon m into x. Okay, so this equation, it is known as equation of SHM. So what is SHM? SHM is simple harmonic motion. Okay, it's a periodic motion which repeats itself in equal intervals of time. All right, so what will happen if you stretch the spring, that is, you pull this block and you release it, it will move back and forth, okay, between some 2 points. Okay, so after that, so this motion is known as SHM, and this is the equation of that simple harmonic motion, or SHM. Okay, so after that you substitute k upon m equals to omega square, or omega equals to square root of k upon m in this equation, and you take this term on left hand side, so you get d2x by dt square plus omega square x is equal to 0. So now most of this chapter is based upon solution of this equation, solution of equation of SHM. Okay, so see, if you solve it, what do you get? So you get an equation for position. Okay, so position is given by a into cos of omega t plus phi. Okay, so the equation for oscillations of this block, it is given by what? A is the amplitude of oscillations, meaning it will oscillate from some point, let's say minus a to plus a. Okay, if you call this initial position of block to be equal to 0, if you call it origin, then it will oscillate between these two positions, minus a and plus a. Okay, so a is the amplitude of oscillation, the maximum distance from its mean position, and then you have cos of omega t plus phi. What is omega t? So omega is equal to what? Square root of k by m. Okay, so we have substituted k by m equals to omega square in this equation. Okay, plus phi. So this phi is known as the phase of oscillations. We'll talk about it. All right. So now this is the equation for position. Then what will be velocity? If you take one derivative of position with respect to time, you get velocity. Okay, so if you take derivative of this cos of omega t plus phi, so you will get minus a omega into sine of omega t plus phi, and then you take one more derivative, you will get acceleration. So what is acceleration? It is dv by dt. Okay, so it is minus a omega square into cos of omega t plus phi. All right, because if you take derivative of sine omega t plus phi, it will be omega multiplied by cos of omega t plus phi. Okay, so that omega multiplied by this omega will give you omega square. And then you can see here you have minus of a times cos of omega t plus phi, which is x into omega square. Okay, so if you substitute a into cos of omega t plus phi equals to x, you get this equation. Okay, a equals to minus omega square x. Okay, so that's the thing from where we started. Okay, so a equals to minus k upon m into x. Okay, so this is our equation, and we have substituted k upon m equals to omega square. Okay, so point is, if you start from this equation, from this solution, you take derivative with respect to time, you get velocity. Then you take one more derivative with respect to time, you get acceleration. And acceleration is equal to what? Minus of a omega square cos of omega t plus phi. So if you substitute x equals to a cos of omega t plus phi, you get a equals to minus omega square x, which matches with your initial equation. Okay, so it matches with this equation, and that proves that this is the solution. Okay, so now what is this phi? Okay, so in this solution, this the term inside this bracket omega t plus phi, it is known as the phase. Okay, it's known as what? The phase of oscillations. So what is omega t plus phi? So this is the argument of the cos or sine in this equation, and it is known as the phase. Okay, so that is, this is the angle which will define what? Where is your particle? Where is your mass in SHM? Okay, what is its velocity? What is its acceleration? Everything will be decided by this term. Okay, omega t plus phi. So it is called as the phase of oscillations. Okay, so now if you substitute t equals to 0, okay, so if this is known as what? I'm sorry, this is phase. Okay, let me drink some water. I guess it was coffee. Okay, I hoped it was coffee, but it's early morning and I'm very lazy to make coffee for myself. Anyways, so after that, so phase is given by omega t plus phi. Okay, and if you substitute, if t is equal to 0, what do you get? This first term will be 0, and you will be left with what? Phase equals to phi. So this phi is known as the initial phase of your simple harmonic motion. Okay, phi is known as initial phase of the simple harmonic motion. So after that, now let's see what does this mean. Okay, so at t equals to 0, if you take phi is also equal to 0, then from what position your particle will start? Okay, so let's consider x equals to a into cos of omega t plus phi. Substitute t equals to 0 and phi equals to 0. So for t equals to 0 and phi equals to 0, what will happen? So this is a into cos of, this term is 0 and this term is also 0. So a into cos of 0. What is cos 0? So cos 0 is 1. Okay, alright. So if your initial phase is 0, then okay, cos 0 is 1, yeah, but it is 1 multiplied by a, right? So if your initial phase is equal to what? 0, then your particle starts from the extreme position. Which extreme position? So if you have pulled your particle till this point and released it, okay, the particle or mass, you have pulled it till this point and released it, so it will start from that position. Okay, if what? Phi is equal to 0, it means that particle starts its oscillations from the extreme position. Okay, and then let's consider another case, case 2. Case 2, this is case 1, that a equals to 0, phi equals to 0. Case 2, sorry, case 1 is what? T equals to 0, at t equals to 0, phi is 0. Case 2, at t equals to 0, let's say phi is equal to 90 degrees. Okay, pi by 2. Okay, let's see what happens now. So x equals to, you get a into cos of omega t plus pi by 2. Okay, that is a into sine of omega t. Okay, because cos of omega t plus pi by 2 is sine of omega t, cos of omega t or cos of theta plus 90 degrees is sine of theta. Okay, so you get a sine of omega t, and what does this mean? It means that your particle starts from the mean position. Okay, see how now substitute t equals to 0. So t equals to 0, if you substitute, you will get sine 0 is 0. Okay, this omega t is 0, so you have sine of 0, it is 0, and 0 multiplied by a is also 0, so you get what? X is equal to, sorry, x is equal to 0. So your particle starts from what? The mean position. Okay, so what is the equation of SHM if particle starts from extreme position? Substitute phi is equal to 0. Okay, then you get a cos omega t. And what is the equation of SHM? If it starts from mean position, then it is a sine of omega t. Okay, so I will write this separately. So if particle starts at extreme position, okay, then x is given by what? A into cos of omega t. And if particle starts from mean position, that is x is equal to 0, the particle starts from that position, then x is equal to a into sine of omega t. Okay, then if particle starts at any other position, then I will have some other value. So for the extreme position, phi is equal to 0, so you get simple equation a cos omega t. For mean position, phi is equal to pi by 2, so again you get simple equation x is equal to a sine of omega t. Alright, so this is simple. After that, let's talk about the time period and frequency of SHM. So the time taken to complete one SHM or one oscillation, it is t equals to 2 pi by omega. Okay, so see what will happen when t is equal to 2 pi. Okay, so see this particle goes from here to here, then it returns back at this position, then it moves from here to here, and from this point it will return to the mean position again if it starts from mean position. Okay, this is one complete oscillation. Okay, so from here to here, then from here to here, from here to here, and from here to here. So time taken by particle to complete this one oscillation. Okay, so what will be its position? If it starts from here, after one oscillation, it will end here. If it starts from here, after one oscillation, it will end here again, right? So see, if you substitute, so here if you consider x is equal to a cos of omega t, that means particle starts from the extreme position. Okay, so at t equals to 0, x is equal to a. Okay, at what another time the position will be same? Okay, that's the time period, right? So after what time, okay, the position will be same again. See, particle starts from there, it performs oscillations. So after some time, it will come back to the same position. That is the time required for one oscillation. Okay, so let's say at t equals to capital T, what happens? X is equal to a again. Okay, so let's substitute that. So you get a equals to a into cos of omega capital T. Okay, so then you can cancel out this a, so you get 1 equals to cos of omega t. That means for what angle? Its cos is equal to 1. So omega t must be equal to what? It should be 0 or 2 pi or 4 pi. Okay, so on and so forth. So for omega t equals to 0, the time must be equal to 0, but that is the initial time. We want what? We want time for one oscillation. Okay, so for that, omega t must be equal to what? 2 pi. So if you substitute omega t equals to 2 pi, you get, if you take omega on the other side, you get t equals to 2 pi divided by omega. Okay, so that is the time period. So capital T equals to 2 pi upon omega, and if you substitute the value of omega, okay, the equation for omega, which is square root of k by m, over here in denominator you will get time period equals to 2 pi square root of m divided by k. Okay, after that, the number of oscillations performed per unit time is the frequency of these oscillations. So frequency is 1 upon 2 pi square root of k upon m. It's just reciprocal of the time period. Okay, so omega equals to 2 pi f. Okay, if you take this 2 pi on left hand side, you will get omega equals to 2 pi f, and it is known as the angular frequency of SHM. Okay, after that, okay, I forgot nobody is watching this, so yeah, so I have tendency to say okay, so to get an acknowledgement. Anyways, so we have already defined phase. Okay, phase of SHM. This is the state of oscillation of particle. Okay, so phase is omega t plus phi. Then let's see SHM as projection of the uniform circular motion. Okay, so let's say we have a particle which performs uniform circular motion. Okay, so if you take a particle which is performing uniform circular motion, so what is projection? So let's say your particle is at this point. Okay, you pick any diameter and you draw perpendicular from that point on the diameter. So it meets here, right? Then your particle, since it is moving on a circle, after some time it goes to here, let's say. So you draw a perpendicular on this diameter, then what will happen? So it meets at this point, right? So this perpendicular drawn on any diameter meets at some point, and that point is known as projection. Okay, so this particle is performing uniform circular motion. What is its projection? So if it is here, draw perpendicular on the diameter, any diameter. Okay, I have chosen this one. So then it meets at this point. Okay, so it's like a mirror image of this particle. Okay, so as particle moves from here to here, what happens? If you draw perpendicular from here, okay, it will meet at this point. Then as particle moves, let's say over here, if you draw a perpendicular, it meets at this point, right? So see, as particle is performing uniform circular motion, its mirror image or its projection, it's performing oscillations. Okay, it's going like this. Then as particle will move from here to here, okay, as particle will go, let's say here, what will happen? Let's say here, okay, so its projection will come over here, right? So as particle moving like this, its projection is moving towards left. As it is performing the other half of the circle, its projection is moving, see, its projection is moving towards right. Okay, so as a particle performs uniform circular motion, its projection on any diameter performs what? Oscillations. Okay, then next is the graphical representation of simple harmonic motion. So how does the graph of position versus time, velocity versus time, and acceleration versus time look like? Okay, so this is x equals to a cos of omega t. That means what we have assumed is the particle is starting from the extreme position. So if particle starts from extreme position, then its position versus time graph will look like this. Okay, it oscillates like this. So at x equal to 0, it is at extreme position. So sorry, at t equals to 0, it is at extreme position, that is a. Okay, so it's here and then it oscillates. So its position goes on increasing and decreasing. Okay, so it will start decreasing, right, position with respect to origin. Okay, so it goes like this and again it goes in reverse direction. So what happens, the position becomes negative, okay, with respect to origin. Okay, so it performs oscillations like this. After that, if you take derivative of this, you will get minus a omega into sine omega t. Okay, so this is negative sine, we have negative sine over here, and a omega into sine of omega t. So if you take graph of sine, it goes like this. Okay, but since we have negative sign, it will be reversed. Okay, about this x-axis. Okay, so this is graph of minus a omega sine of omega t. So see how much is the amplitude? A omega is the amplitude. Amplitude for position is a. And if you take one more derivative of this, you will get formula for acceleration minus a omega square cos of omega t. So see, apart from the amplitude, let's say if you keep omega equals to 1, this will become what? Plus a and minus a. What will you get? So it is mirror image of this graph about the x-axis. Okay, so here if you have displacement above the x-axis, here you will have same displacement below x-axis. Okay, so this is the graphical representation of SHM, simple harmonic motion. Okay, and this is for particular case when particle starts from extreme position. If particle starts from mean position, then you will have sine curve. All right, after that, let's talk about the energy in SHM. So the potential energy of SHM is half of k into x square, and it's basically the potential energy of the spring. Okay, then if you substitute k equals to m omega square, you will get half of m omega square x square. So we have to memorize this formula as well as this formula. Okay, then kinetic energy is given by half of m into v square. So if you substitute this equation for velocity over here into v square, you will get half of m omega square a square sine square omega t plus phi. Okay, considering some initial phase phi. Okay, then what is this thing? So sine can be written as what? It can be written as 1 minus cos, right? So you can substitute, like sine is equal to what? 1 minus cos. Okay, not sine, sine square can be written as 1 minus cos square, right? So if you do that, you end up with this formula. So you get kinetic energy equals to half of m into omega square into a square minus x square, right? Half of m omega square a square minus x square, you get this formula. Okay, and if you add these two, potential energy plus kinetic energy, okay, so this x square and this minus x square, because the coefficient is common, half of m omega square, half of m omega square. So x square and minus x square will get cancelled out, and if you add it up, what you will get is half of m omega square a square. This x square and minus x square gets cancelled out. Okay. So yeah, so you get total energy of SHM equals to half of m omega square a square of half of k into a square. Okay, and this is the graph of potential energy, kinetic energy, and the total energy. So total energy remains constant. So as particle is at mean position, its potential energy will be equal to 0. Okay, because potential energy is what? It is half of m omega square or k into x square. So if particle is at mean position, x is equal to 0, so potential energy is equal to 0. So its total energy is kinetic energy, and this tells you that particle has maximum velocity at the mean position. Okay, and then when particle is at extreme position, its potential energy will be what? It will be half of m omega square x square. Okay, that is x is equal to a, so it is half of m omega square a square. Okay, when particle is at extreme position, the potential energy is half of m omega square a square. That means its total energy is just potential energy, it doesn't have any kinetic energy, and that's why particle is at rest at both the extreme positions. So it will be rest on extreme position on right, and it will be rest on the extreme position on the left also. Okay, so yes, this is the total energy of SHM, simple harmonic motion. And then from simple harmonic motion, let's talk about the simple pendulum. Okay, so pendulum oscillates like this, so its motion can be also called as the simple harmonic motion. Okay, so if you take a pendulum like this, if you pull it apart, okay, from its equilibrium position, so let's say you pull it till this point and this theta is small, so there will be one force acting on it, that is the gravitational force. Okay, there is another force which is tension in the string. All right, so this gravitational force mg can be resolved into two components. Since this angle is theta, this angle is also theta, because these two are parallel lines and this is an intercept. Okay, so these are corresponding angles and corresponding angles are equal. So this angle is theta, this angle has to be theta. So then the weight of this bob of pendulum is mg. You can resolve it along two components. So one component is along this line, so it is mg cos theta, and another component is perpendicular to it, so it is mg sine of theta. Okay, this one is mg cos theta, this is mg sine theta. And why is the negative sign? So now negative sign has to do with the direction. Okay, so what you have done is you have displaced it towards right, and the force, the component of this gravitational force or the weight, it is acting in this direction. Okay, so it acts like a restoring force, it wants to restore the pendulum back to its mean position. Okay, and that's why that negative sign is there. Okay, so the restoring force is equal to what? Minus of mg sine theta. And then for small angles, if theta is very small, then we know, or we have to know, that sine theta is nearly equal to theta, and it's nearly equal to tan of theta also. Okay, so sine theta is nearly equal to theta, and if you measure theta over here, so this can be called as displacement x. Okay, so arc is the displacement and L is the length of this pendulum. So x upon L will give you what? Theta. All right, so sine theta is nearly equal to theta, and that is equal to what? Displacement from here to here divided by L, because we know angle is equal to arc upon radius, right? So if you consider this as a part of a circle, then this is the arc and this is the radius. So it is x upon L. Okay, and then you can write force is equal to mass into acceleration over here. So this m and this m gets cancelled out. You have substituted sine theta equals to x upon L. So this m and m gets cancelled out, and you get a equals to minus of g upon L times x. Okay, similar to what you got in case of a spring, a mass connected to spring. In that case, you had a equals to what? Minus of k upon m into x. In this case, you have minus of g upon L into x. So it's similar to that case. What you are going to do is the term that was here. In earlier case, it was k upon L. In this case, it's g upon L. Okay. So k upon m you replaced with what? Omega square. So this g upon L you will replace with what? Omega square. So omega square is g upon L. If you substitute that, you get acceleration is d2x by dt square. So d2x by dt square equals to this term, we are calling it omega square. So it is minus of omega square into x. Okay. And then if this is omega square, what is omega? It is square root of that. So omega equals to square root of g upon L. So this is exactly similar to the earlier equation of SHM. And if you solve this, you will get equation for the position, velocity and acceleration of this bob of the pendulum. Okay. So we are interested in frequency and time period. So if omega is equal to g upon L, we have seen that omega can be written as 2 pi f. Okay. So omega equals to 2 pi f. If you take 2 pi on other side, what do you get? Frequency of a pendulum is 1 upon 2 pi square root of g upon L. And if you take its reciprocal, you will get time period of oscillations of this pendulum, which is 2 pi square root of L upon g. Okay. Yes. So that was the simple pendulum. Okay. Then let's talk about damped simple harmonic motion. And I would like to tell one thing, that most of the questions that were asked on oscillations, they were asked till this point. Okay. So I guess most important theory is till this point. And there were very few questions or close to zero questions asked on damped harmonic motion and post damped harmonic motion. Okay. Anyways, let's talk about this in very short. So if you have this block, okay, connected to a spring, you will stretch it, release it. What will happen? It will perform oscillation. But now there is some addition. Okay. So in earlier case, we neglected medium. Now we are considering that there is some medium which is present. Okay. So if there is nothing, air will be there, right? So there is some medium. So what happens when this block performs oscillations in the air or any medium, then there will be some damping force, some drag force acting on it. Okay. So if there is air, that block wants to move through the air, that air will resist it. And that resisting force, it is given by minus of B into V. The resisting force is directly proportional to velocity and B is the constant. Okay. So this is damping force due to the surrounding medium, and B is what? B is the damping constant. Okay. So now there are two forces acting on this block. So how much is the net force? Net force is addition of these two. So it is equal to what? Minus of B into V, okay, which is damping force, and there is restoring spring force acting on it too. So minus of K into X. Okay. Then you substitute force equals to mass into acceleration. So you get m into d2x by dt square. Okay, mass into acceleration. Since acceleration is d2x by dt square, you get m into d2x by dt square, plus you have these two terms on right hand side, they have negative signs. If you take them on left hand side, their sign will be positive. Okay, so you take them on left hand side and you also substitute v equals to what? Dx by dt, rate of change of position with respect to time. So you get this equation. So this is the equation of a damped harmonic oscillator, damped simple harmonic oscillator. Okay, and if you solve this, you get this solution. Okay, which is similar to the solution of simple harmonic oscillator, but there is one difference. The amplitude of damped harmonic oscillation is this much. Okay, so you can see here it is some amplitude. So this is the initial amplitude, and then you have a term in multiplication with that a. So it is e raised to minus bt divided by 2m, and this term says as time increases, what will happen? The magnitude of this term will decrease. Okay, so at t is equal to 0, e raised to 0 or anything raised to 0 is 1. Okay, so at t equals to 0, the amplitude will be what? So it is equal to a because value of this term is 1. So as t increases, you have negative exponent of the exponential of e. Okay, so as t increases, the value of this thing will decrease. So initially it's 1, then it goes on decreasing. Let's say 0.9, 0.8, okay, 0.7, etc., etc. So your amplitude, this is the total amplitude, it goes on decreasing. Okay, so that's why it is called as damped simple harmonic oscillator. Its amplitude gets damped. Okay, it goes on decreasing, and it oscillates with this frequency. So initially the frequency, I mean in case of simple harmonic oscillator, the frequency was omega equals to square root of k by m, the angular frequency. Here now the angular frequency will become omega dash, omega prime, and that omega prime has this value, square root of k by m, but there is an additional term, okay, minus b square upon 4 m square. Okay, where b is what? B is the damping constant, okay, and m is the mass of this oscillator. Okay, m is the mass of this block. All right, so it will oscillate with the reduced frequency. See, because initially the frequency was square root of k by m. Now we are subtracting something from this square root of k by m. So its amplitude goes on decreasing as time passes, and its frequency is also reduced compared to the earlier case. So the effect of medium is it decreases the amplitude of oscillations, and after some time at t equals to infinity, let's say, the amplitude will die out. So because the medium is resisting this oscillation, so amplitude will go on decreasing and finally it will become 0. So this block will stop oscillating. Okay, and its frequency of oscillations is also reduced compared to what? The earlier case, the simple harmonic motion, because now the medium is also resisting it. Okay, so this is the damped simple harmonic motion. And then there is one more thing, the forced oscillations. Okay, or you can call it forced damped simple harmonic motion. Okay, in full. So let's say there is an extra force acting on this oscillator. So there is spring force, which is the restoring force, which is causing the oscillations. There is force due to medium, which is resisting the oscillations, and you are pulling it, let's say, with a periodic force. Okay, you are exerting an extra force. Okay, then the motion that you get, it is known as the forced damped simple harmonic motion. Okay, if you remove medium, then it will be forced simple harmonic motion. All right, so this is the periodic force. Okay, f naught cos of omega d into t. Okay, omega d is the frequency of this periodic force. All right, so now what will be the net force acting on the particle? So there are three forces. So mass into acceleration of this block or a particle performing SHM. So there are three forces acting on it. So what are those three forces? First is the spring force. Okay, then next is the damping force due to the medium. Okay, we have seen it in last case, minus dV, plus there is external force, external periodic force. Okay, What do you mean by periodic? It will keep on increasing, decreasing. All right, and it will reverse its direction also. So it is the external periodic force F of t is F naught cos of omega d into t. Okay, then its solution, it is given by a into cos of omega dt plus pi. So what will happen here is initially it will oscillate with some frequency. Initially it will try to oscillate with its natural frequency, but since there is a medium which opposes that natural frequency and there is an extra force, okay, the external force, so finally what that block has to do is it has to get adapted to the external periodic force and it will oscillate with the frequency of the external periodic force. Okay, so that's why this is the solution, but this is not the solution at beginning. Okay, this is solution at infinity. After some time passes, what happens? The block gets adapted to the frequency of the external periodic force. Okay, and then this the amplitude. Now this formula for the amplitude is quite complicated, but I don't think there will be a direct question on this. Okay, so formula for amplitude is F naught divided by m square into omega square minus omega d square. And remember what is omega? It is square root of k by m. And what is omega d? It is the frequency of the angular frequency of external periodic force. Okay, plus omega d square b square. Okay, bracket complete, raised to half. Okay, where b is what? Damping constant. All right, and now, so in this thing, the more important cases are, first one is small damping, okay, and the driving frequency is far from natural frequency, and second thing, this driving frequency is close to natural frequency. So this is the most important thing. Okay, this is called resonance. All right, so for small damping, there is no damping, let's say. Okay, very small damping, you can neglect this b in the denominator if you neglect the medium. So there is an oscillator and there is an external force. Okay, so in that case a is equal to what? F naught divided by m into omega square minus omega d square. Okay, all right, and if driving frequency is close to natural frequency, so this is particularly important case. If driving frequency is close to the natural frequency, then what will happen? That means frequency of external periodic force which is oscillating that block is close to the natural frequency of oscillation. Then the block will oscillate with the maximum possible amplitude, and this case is known as the resonance. Okay, so when the driving frequency matches the frequency of the oscillator, this case is known as what? Resonance. All right, so oscillator oscillates with maximum amplitude. This is the summary. Okay, so when driving frequency matches the natural frequency of oscillation of an oscillator, or let's say that spring, then the spring will oscillate and therefore the mass will oscillate with the maximum possible frequency. Okay, sorry, maximum possible amplitude. Okay, so amplitude of oscillations will be maximum at, and it is given by this formula F naught upon omega d into b. Okay, so this is called as resonance. All right, and then there are some trigonometric formulae. So if you know this formulae, then some of the questions will be handy. Okay, not all of these formulae. So you need to know the addition of two angles, formulae for sine and cos of addition and subtraction of two angles. Okay, tan you need not know. Okay, so now these two. So I'm erasing it because I'm going to provide this as notes. And then what else? So tan you need not know. All right, so tan you need not know. So remaining formulae you need to know. Okay, out of following functions representing motion of particle, which represents SHM? So we have to find out which of the following is SHM. Okay, so first one is y equals to sine of omega t minus cos of omega t. So this is definitely SHM. Okay, this is combination of two SHM. So first is SHM. Second one, let's see y equals to sine cube omega t. Okay, so y is equal to sine cube omega t. Let's see the formula for sine cube. So there is, okay, this formula. If you see over here, sine 3a equals to 3 sine a minus 4 sine cube a. Okay, so sine 3 theta equals to 3 sine theta minus 4 sine cube theta. So if you want formula for sine cube, so sine cube theta will be equal to what? 3 sine theta minus sine 3 theta. Okay, and this 4 will go into denominator upon 4. Okay, so I have just rearranged this formula and I got this formula. So see, theta is omega t over here, y is equal to sine cube of omega t. So it is 3 sine of omega t, theta is omega t, right, minus sine of 3 omega t. Okay, so yes, this is what 3 sine omega t, theta is omega t, minus sine of 3 omega t divided by, you have 4, but you don't have to think about it. Okay, actually it is in denominator of all this, right? So see over here that first one, okay, you have SHM with frequency omega t. Okay, then you have another SHM with frequency 3 omega t. So this will be some kind of periodic motion. Okay, it's addition of two SHM at different frequencies. Okay, this is the problem, and that's why the resultant will not be a simple harmonic motion with one frequency. Okay, so this is addition of two different SHMs with different frequencies. So if you add them, their addition will not be an SHM. If frequency is same, then phase will change, but the particle will perform oscillations, okay, with same frequency, like what we have in first case. It is addition of two SHMs with same frequency, so resultant will be an SHM with the same frequency. Okay, so here since frequency is different, this is not an SHM, this is not an SHM. After that, next we have y equals to 5 cos of 3 pi by 4 minus 3 omega t. So this is also SHM. Okay, 4 is clearly not an SHM. Fourth, it is 1 plus omega t plus omega square t square. This is clearly not SHM. And if you think about third, okay, third is y equals to 5 cos, and now I will just write it as 3 omega t minus 3 pi by 4, and we know cos of minus theta is equal to cos of theta. Okay, so there is no harm in doing this, but we need to know this, that cos of minus theta is equal to cos of theta, sine of minus theta is minus sine theta. Okay, so it is 3 omega t minus 3 pi by 4. So you can multiply this argument of cos with negative sign and it makes no difference. Okay, so then it is simple. This is a simple harmonic motion with frequency, angular frequency 3 omega. Okay, instead of omega we have 3 omega. All right, so this is also SHM. Okay, so out of these, one is SHM, third is SHM. So which option matches with this? Only 1, only 4 does not represent SHM. Only 1 and 3, right? 1 and 3rd, they represent simple harmonic motion. Option C is the answer. Okay. All right. Then yes. So let's move on to the next problem. So the displacement of particle along the x-axis is given by x is equal to a sine square omega t. The motion of particle corresponds to, it is sine square omega t. Okay, and here we have to be careful. So we need to remember many formulae over here, and one of the formula is, see, cos of 2 theta can be written as 1 minus sine square, okay, theta, okay, so 1 minus cos of 2 theta, yeah, so formula is like this. So sine square theta can be written as 1 minus cos of 2 theta upon 2, okay, and that's what exactly we want. All right, so this is the formula that we need to remember over here. So sine square omega t, okay, the sine square omega t can be written as 1 minus cos of 2 omega t divided by 2. So this can be written as, see, theta is equal to omega t, x is equal to a multiplied by 1 minus cos of 2 omega t divided by 2. Okay, see over here, sine square can be written as what? 1 minus cos 2 theta upon 2, and put theta equals to omega t. So you get this equation. And then you can write this as a by 2 minus half of cos of 2 omega t. So first term is just some initial displacement. Okay, so you can forget that, it's a constant term. And then if you look at second term, you get half, okay, you have a in multiplication also, a by 2 into cos of 2 omega t. So this is an oscillatory motion with amplitude equals to a by 2, and the frequency, the angular frequency, equals to 2 omega, right? So this is a simple harmonic motion. And how much is the frequency? Okay, they want frequency, right? So omega dash, the angular frequency, is 2 omega, right? It is the simple harmonic motion with angular frequency 2 omega, and you can write omega prime equals to 2 pi f dash. So that's 2 omega. Okay, so you can cancel out this 2 and 2, okay, and take pi on the other side. So you get f dash equals to omega upon pi. Okay, and that's the option A. So the answer is, it is simple harmonic motion of frequency omega divided by pi. This is the answer, option A. Okay, so is it clear? All right, so let's move on to the next problem. A particle executes simple harmonic oscillation with an amplitude A. The period of oscillation is capital T. The minimum time taken by particle to travel half of the amplitude from the equilibrium position is, okay, so particle performs simple harmonic motion, that's given. Amplitude is A, oscillation period is T. The minimum time taken by particle to travel half of the amplitude from the equilibrium position is, okay, this is the question. So particle starts from equilibrium position. Okay, this is the moral of the story. So we have to use which equation? X is equal to A into sine of omega t, and at some time t, what happens? X is equal to A by 2. So the particle travels to half of the amplitude. So we have to substitute that. So it is A by 2 equals to A sine of omega t. So A and A gets cancelled out. So you get, half equals to sine of omega t. So sine of omega t equals to half. Okay, and for which angle its sine is half? So we know it is 30 degrees, right? So sine 30 is half. Okay, the minimum angle for which sine is half, sine of that angle is half, it is 30 degrees. Why minimum? Because we want the minimum time, okay, the minimum time in which this particle travels half of the amplitude. So we want minimum time, that's why we are taking minimum angle. Okay, so it is equal to sine of, this is equal to what, sine of 30 degrees and 30 degrees. So pi equals to 180, 180 divided by 6 will give you 30 degrees. It is sine of pi by 6 is equal to sine of omega t. Okay, and then therefore omega t is equal to pi by 6. So omega can be written as 2 pi upon capital T. Okay, omega is 2 pi upon capital T. So that multiplied by t is equal to pi by 6. So pi and pi gets cancelled out, and you take this t and 2 on the other side. So what do you get? So you get this 2 goes in denominator, right? So you get t equals to capital T will go in numerator on the other side, capital T divided by 6 times 2, that is 12. Okay, so this is the answer. So yes, option B is the answer. Okay, is it clear? Clear, not clear? All right. So let's move on to the next problem. The next problem is the radius of a circle, the period of revolution, initial position, and sense of revolution are indicated in the figure. The radius of circle is, okay, it's 3 meters. It is revolving in anticlockwise sense. At t equals to 0, it is at this point, and at capital T equals to 4, okay, it is at some point. Okay, sorry, capital T equals to 4, this is the period. Okay, yeah. So then y projection of the radius vector of rotating particle p is, okay, so we want y projection of this particle. So now see, the particle is rotating starting from here, okay, from here in clockwise sense, right? In clockwise sense, it is given over here. So after time t, okay, I will draw that circle again over here. So after time t, let's suppose particle moves from there to here. And we want its y projection. So this is the angle omega t, right? In time t, it covers, it's moving with angular frequency omega. The particle is moving with angular frequency omega. So in time t, it will move with angle omega t, because omega equals to, if we recall from circular motion, omega is theta upon t. So theta equals to omega t, right? So if you draw a perpendicular from here, you will get y projection. Okay, so this is r, and if you resolve it in two components, so this will be r cos omega t. So clearly this is the cos component. Okay, the y projection is cos component. All right, so let's see which are cos options. So okay, so there are three options. All right, and then which of these is matching? So it is above the x-axis, so it cannot be negative, because if you substitute t equals to 0, cos of this, cos of 0 will be 1, and you will get minus 3. So it's not starting from this position, it's not minus 3 at the beginning, it is starting from plus 3. So this is also not possible, sine is not there. Okay, so this projection is cos component. Okay, so this is not possible. So you have these two options left. So let's check which of these two is correct. So for that we have to find what? omega. Omega t equals to what? So omega t is equal to 2 pi capital T upon T, and that is equal to 2 pi capital T divided by, 2 pi small t upon capital T. So 2 pi T upon capital T is 4. Time period is 4. So let's substitute that. Let's substitute time period is equal to 4. So you get 4 by 2. This 4 divided by 2 gives 2 in the denominator. So you have pi t upon 2. Okay. So omega t should be pi t upon 2. So this is the answer, not this one. Here it is 3 pi t upon 2. So this is the answer. Option A. Okay. So this was a simple problem, provided you know how to look at it. All right. So this is a simple problem. Let's move on to the next one. So the phase difference between displacement and acceleration of a particle in SHM is. So this we discussed in the beginning. So see, displacement is given by x is equal to, let's say, a cos of omega t. Then acceleration of the particle is given by minus of a omega square into cos of omega t, or it is minus of a omega square, or a into cos of omega t you can write as x. So it is minus of omega square x. Okay, this is the relation between the acceleration and the position. So how much is phase difference is the question. Okay, so since there is negative sign, the phase difference would be pi. Okay, see, so since there is negative sign, how much would be phase difference? It will be pi, because let's say you have another equation. This is x is equal to a cos of omega t, and you have x equals to a into cos of omega t plus pi. When will you end up, at what value of pi will you end up with the negative sign minus of a over here? So let's say t is equal to 0. Okay, so for what value of pi, okay, will you end up getting negative sign? So cos of pi equals to minus 1, right? So let's say t is equal to 0. So for t equals to 0, you will get what? I'm sorry, I will write it here. So for t equals to 0, will give you a, because cos 0 is 1. Okay, so here let's say it is a is equal to minus of omega square x, right? So you want negative sign, okay, in front of x. So if you consider that x is equal to omega t plus some pi, okay, so for what value of pi you will get a negative sign over here. This is the question. So put t equals to 0. So you get a into cos of pi. Okay, so phi equals to, if phi is equal to 180, you will get what? Cos of 180 or cos of pi is minus 1, and that means the phase pi gives what? Phase pi gives what? Negative sign. So what is phase difference between x and a? Since you have negative sign over here, since a is equal to minus of some constant into x, that means the phase of a, it is how much is difference between phase of a and x? It is what? 180 degrees, or it is pi. Okay, so pi. And now here we can memorize few things. So phase difference between, see, x is equal to a into cos of omega t, then v equals to, we get minus a omega into sine of omega t. Okay, so you go from cos to sine. How much is the phase difference? Phase difference will be pi by 2. And then again you go from sine to cos, because a is equal to what? Minus of a omega square into cos of omega t. So you go from sine to cos. Once again, there will be phase shift of pi by 2. So pi by 2 plus pi by 2 equals to what? Pi. So we can remember this, we can memorize this, that the phase difference between position and velocity is pi by 2, and phase difference between the velocity and acceleration is pi by 2. So therefore phase difference between position and acceleration is what? Pi. Okay. Yeah, so nobody is watching this. Anyways, let's move on to the next problem. And next problem is from NEET 2019. Average velocity of a particle executing SHM in one complete vibration is, this is the question. So how much is average velocity? This is actually the most simple question asked in NEET on SHM. So see, if you consider one oscillation, particle starts from some position, it ends at the same position, right? So since it ends at the same position, it does not displace. So there is no displacement, and since there is no displacement, it's, what is velocity? It is displacement divided by time. And since there is no displacement, displacement is zero, so velocity is also zero. So average velocity of SHM is what? It is zero. Okay. All right. Let's move on to next problem. Okay, so next problem is a particle is executing a simple harmonic motion. Its maximum acceleration is alpha and maximum velocity is beta. Then its time period of vibration will be. Okay, particle is executing simple harmonic motion. Maximum acceleration is alpha. So see, what is acceleration? It is omega square x. And what is velocity? With sign, it is minus of omega square x. And velocity, okay, the amplitude of velocity is what? It is a omega. Okay, so now I just want maximum values. Okay, so I will just write, see, x is equal to a into cos of omega t, v equals to minus a omega into sine of omega t, and acceleration is equal to minus omega square x. Okay, so I want maximum value. Okay, so what will be maximum value? I'm sorry, of velocity. So maximum value Vmax is equal to what? So sine of omega t will be equal to 1, because maximum value of sine or cos is equal to 1. So sine of omega t, let's consider it to be equal to 1. So we get a omega. Let's forget the sine. Okay, so a omega is the maximum value. What is maximum value of acceleration? So x, what is maximum value of x? It is a, because cos of omega t will be equal to 1 for maximum value. Okay, so maximum value of cos omega t is also 1. Sine or cos, maximum value is 1. So maximum value of acceleration is when x is maximum, that is, it is at the extreme position. So a is equal to omega square a, capital A. Okay, so this is a max, maximum value, and it's given in the question that its maximum acceleration is alpha. So this is equal to alpha, and maximum velocity is beta. So this is equal to beta. Okay, and we want its period of vibration. Okay, so we want its period of vibration. So let's divide these two equations. Okay, so if I take alpha upon beta or beta upon alpha, whichever way, so I will take alpha upon beta, I will get omega square a, this is alpha, divided by a omega, this is beta. So omega and one of the omega gets cancelled, a and a gets cancelled, and we want what? We want time period. So we have to substitute this remaining omega as what? 2 pi divided by t. So this is equal to 2 pi upon t is alpha upon beta. So let's take t on left hand side, alpha beta on right hand side. So what do we get? So it implies that t is equal to, t will go in numerator, so this beta goes on numerator, in numerator on other side, and alpha goes in denominator, right? So it is 2 pi beta divided by alpha. Okay, this is the answer. So option B is the answer. Okay, yes. So let's move on to the next problem. Next problem is the oscillation of a body on a smooth horizontal surface is represented by equation. So this is the equation. X is a cos omega t. Okay, so when we read this equation, one thing should pop up in our minds, that the particle is starting from the extreme position. Okay, so which of the following graphs shows correctly the variation of A with respect to t? So here, all right. So since it starts from extreme position and it starts from positive extreme position, so this is the straightforward question, very straightforward. So it should be either it should be at plus A. So only this one, right? So here it is starting from minus A. Here it's starting from origin. Here it's starting from origin. Okay, not this one, not this one, not this one. There is only one correct answer, which is this one. Okay. See, x is equal to a cos omega t. Particle starts from positive extreme position. All right. If it is minus a cos omega t, it will be particle starting from negative extreme position. If it is a sin omega t, then particle starts from the mean position and it moves towards right. Okay. All right. So this is simple. Then next question. Two simple harmonic motions of angular frequency 100 and 1000 radians per second have same displacement amplitude. The ratio of their maximum acceleration is, okay, so angular frequency is given, so omega 1 equals to 100, omega 2 equals to 1000. And what's the question? They have same displacement amplitude also. Okay, and the question is the ratio of their maximum acceleration is. So maximum acceleration, a max, as we saw in the last problem, it is omega square a, right? So for first one, let's call it a1 max and a2 max. A1 max equals to omega 1 square a1. A2 max will be what? Omega 2 square a2. And we want ratio of this maximum acceleration. So let's divide this. So what do we get? Okay. So a1 max upon a2 max is equal to, see, it's given that the displacement amplitude is same. So a1 is equal to a2. So we can cancel it out, right? Then it is omega 1 square upon omega 2 square. So it is 100, I'm sorry, 100 upon 1000 square of this. Okay, omega 1 upon omega 2 square of that. So yes, 100 divided by 1000 is 1 by 10 and square of that will be 1 by 100. Okay, so this is equal to 1 by 100. So which option is correct? This one is correct, option D. Okay, so this was simple. This was very simple. All right, let's move on to next problem. A point performs simple harmonic oscillation of period t and equation of motion is given by this thing. After the elapse of what fraction of time period, the velocity of point will be equal to half of its maximum velocity. Okay, so question is, at what fraction of time the velocity will be half of the maximum velocity? This is the question. Okay, so let's solve this. So we want velocity, which is dx by dt, right? It is d by dt of x, which is a into sine of omega t plus pi by 6. Okay, so that is Now if we take derivative of this, what do we get? So a is constant, it will come outside. So a into d by dt of sine of omega t plus pi by 6, right? And derivative of sine will give us cos, okay, but we don't have t over here. It's not derivative of t with respect to t, it's derivative of omega t with respect to t, okay. So it will be a omega into derivative of omega t with respect to omega t. All right, this is chain rule of derivatives, if you remember this, okay. So we have coefficient omega in multiplication of t and we want to take derivative with respect to t. So we can write this as omega times, okay, cos of omega t plus pi by 6. This will be the derivative. All right. So this is v, and we want time t when v is equal to what? Half of its maximum value. Okay, how much? Half of the maximum value will be equal to half of the maximum value. So v is equal to v max upon 2. Okay, v max maximum value divided by 2. What is the maximum value? So the coefficient of this cos term that you see here is the maximum value. Okay, so it is a omega upon 2. So let's substitute that over here. So what do we get? So we get a omega upon 2. This is the value of v. It is equal to a omega into cos of omega t plus pi by 6. Okay. So this thing gets cancelled out. A omega and a omega gets cancelled out, and we are left with cos of some angle, which is equal to half. Cos of omega t plus half, pi by 6 is equal to half. So what is, for which angle its cos is equal to half? Sine 30 is half, that is cos 60 is half. Okay, so cos of 60 degrees is equal to half. This we must know. So what is 60 degrees? So 60 degrees is pi by 3 because pi is 180. So this is equal to what? Cos of pi by 3 is cos of omega t plus pi by 6. That means omega t plus pi by 6 is equal to what? It's equal to pi by 3. So we can take that pi by 6 on other side. So we get omega t is equal to pi by 3 minus pi by 6, or omega can be written as 2 pi upon capital T. Okay, omega is 2 pi upon capital T. So pi by 3 minus pi by 6. So this pi by 3 can be written as 2 pi upon 6. Okay, multiplying by 2 and dividing by 2. So 2 pi by 6 minus pi by 6 is pi by 6. Okay, and then we can move this. We can move this t on other side, 2 pi on other side. Before that, we can cancel out pi actually. So pi gets cancelled out. So we can move this t and 2 on other side. T goes in numerator, 2 goes in denominator. So we get t equals to t divided by 6 times 2, that is 12. So this is the answer. Okay. So option B is the answer. All right. This was simple. Very, very simple. Let's move on to next problem. The phase difference between the instantaneous velocity and acceleration of particle executing simple harmonic motion is. So we discussed this. The phase difference between displacement and velocity is pi by 2. Phase difference between velocity and acceleration is pi by 2. Okay. So how much is the answer? It's pi by 2 or 0.5 pi is the answer. Very, very straightforward, very, very simple question. Okay, let's move on to next question. Which of the following equations of motion represent simple harmonic motion. So acceleration is minus, okay, so we know acceleration in simple harmonic motion is equal to what? Minus of some constant, okay, some constant, okay, multiplied by x, right? So here, let's check the options. Option A is minus of k into x plus a. This is not SHM, okay? So SHM is always what? Acceleration is some constant into x, not x plus a. It doesn't depend on the initial position. Acceleration does not depend on the initial position, okay? Acceleration is k into, here sign is positive, so this is not possible. Acceleration kx, again not true, it is minus some constant into x, okay, right? Acceleration is minus of omega square x, so omega square is some positive constant. And then last one, acceleration is minus k naught into x, okay, but there is one term in addition which is k1 into x square, so this is also not true. So none of the options is true, and there is no option like that, unfortunately. So answer is none of these options is correct. This is the answer. Okay. All right. Then let's move on to next problem. Next problem is a particle of mass m is released from rest and follows a parabolic path as shown. Okay. It released from rest and it follows this parabolic path. It moves in this parabolic path. Assuming that the displacement of mass from origin is small, displacement is small, that means it performs oscillation, okay, through and fro, to and fro like this. Which graph correctly depicts the position of particle as function of time? So the answer is simple. It must be option A, because unless you displace it, it won't perform oscillations. Okay, so this is not the graph for simple harmonic motion. This is also not graph for simple harmonic motion. There are two possible answers, out of which, okay, out of which this must be true, not this one, because in this case it starts from origin. So if you have a bowl like this and you have a ball in that bowl, so if it is at rest at the origin, okay, at the midpoint of the bowl, at the center of the bowl, it will not perform oscillations. You have to displace it, then only it will perform oscillations. Okay, so in last one it starts from the mean position. It cannot be true. So what is true is option A. Okay, this is again very simple question. The next question, the particle executing simple harmonic motion has a kinetic energy. This thing, the maximum values of potential energy and total energy are respectively. So see, we know that, okay, kinetic energy is given by this formula k naught cos square omega t. Okay, so maximum value of kinetic energy, let's find out. It's k naught, because cos of omega t, its maximum value is 1. Okay, and then if we recall the curve, this curve, sorry, the relation between potential energy, this is potential energy, okay, curve, then we have kinetic energy curve. So kinetic energy is maximum when potential energy is 0. Potential energy is maximum when kinetic energy is 0. And addition of those two is constant. The total energy is constant. And how much is total energy? Let's say it is this much. Okay. So how much is the magnitude of total energy? It's this much. So See, at this point the kinetic energy is maximum, okay, and potential energy is 0. So maximum value of kinetic energy is equal to what? The total energy. Okay, so that is, at this point the kinetic energy is maximum, its value is k naught. So how much is total energy for this one? It's k naught. And how much is maximum value of potential energy? So see, over here kinetic energy becomes 0, so its total energy becomes potential energy, that is this much. Okay, the same value, so it's also k naught. So the maximum values of total energy and potential energy are k naught and k naught respectively. All right, so very straightforward, very simple question. All right, let's see this next question. A pendulum is hung from roof of sufficiently high building and is moving freely to and fro like a simple harmonic oscillator. Okay, the acceleration of bob of pendulum is 20 meters per second at a distance of 5 meters from the mean position. Okay, the time period of oscillations is, all right, so we are given that acceleration is equal to 20 meters per second square when x is equal to 5 meters. So we know the relation between acceleration and position. So a is equal to minus of omega square x, but we want only the magnitude. Okay, so the magnitude of a, because the direction is not given, it is omega square magnitude of x. So we get omega square equals to magnitude of a upon x. Okay, so magnitude of a upon magnitude of x, and that is 20 divided by 5, it is 4. We want time period, right? So omega square is 4, that means omega is equal to 2. Okay, so 2 pi by t is equal to 2. So this 2 and 2, what happened? Oh, so this 2 and 2 gets cancelled out, and we get, if we take t on the other side, we get t equals to pi. So answer is what? T equals to pi. So this is the answer. Option B is the answer. All right.